In this video, we're going to be talking about ethers, epoxides, amines, and thiols in effort to finish out Chapter 11 so that we can do all the homework for recitation on Wednesday. Alcohols and ethers are very similar in that they have similar leaving groups. So just like in the beginning of the chapter when we talked about OH itself not wanting to leave, so is it that OR does not want to leave either. So in order to actually make both of these groups leave, we're going to need to activate it. The leaving group of an ether can be activated by protonation, just like in the alcohol chapter. So if we have an ether and that's the group that we want to leave, we will react it with HI, acid. The ether gets protonated. We can have substitution with the halide. The mechanism of that reaction is very similar to what we learned in the beginning of the chapter with alcohols. Here we have the ether oxygen gets protonated, so that reaches out and forms a bond with the hydrogen. The two electrons here hop onto the iodine. In the second step, we have this protonated ether, which now becomes an alcohol leaving group. So the methanol, or the alcohol, leaves. We form a carbocation on that carbon right there. This is an SN1, because this was tertiary ether. And then we can have the I- come and be the nucleophile and attack the carbocation, giving us this new alkyl halide and an alcohol, which was the leaving group. If a relatively stable carbocation is formed when the alcohol leaves, then it will be an SN1 reaction. And that's the case with tertiary carbocations. Now here's an example of SN2. We have our ether. It gets protonated in the same way. Then we have this protonated ether, which is actually an alcohol leaving group, and in an SN2 mechanism, because this is primary, so there's a lot of room. The I- does backside attack and kicks out our alcohol. This is an SN2 reaction, so we end up with our alkyl halide here and our alcohol. It turns out the ethers undergo SN1 reactions unless they form a primary or methyl carbocation. Ethers cannot be activated by other methods. Remember, we had a bunch of different reagents that could activate the alcohol earlier in this chapter, but those do not work for ethers. And so because the ether forms an intermediate that cannot lose a proton, it is not possible to use these special activators. Ethers are very typically solvents because they only react with hydrogen halides. And so they're polar, at least a little bit polar, because they have a dipole with that oxygen in there, but they're not reactive. Epoxide. Now remember, epoxide is that three-membered ring with the oxygen in it. It is an ether, but it's a special ether. And the reason it's a special ether is because it's so reactive because of the ring strain. Remember how we made these epoxides back in an earlier chapter. When we had an alkene, we reacted that with peroxy acid, shown here. We end up with the epoxide. And then we also got a carboxylic acid as a side product. Once we form the epoxide, there's a lot we can do with it, and that's what this chapter is about. Recall synthesis of an epoxide. One way to make an epoxide is to take a double bond, do hydrohalogenation, so we have a chlorine and a OH in the trans position. Then we use sodium hydride to pull off that proton so that we have this species right here. And then we can have intramolecular SN2, or literally backside attack, so we have this oxygen reach out there and kick the chlorine out to make an epoxide. Epoxides are more reactive than ethers because of the ring strain. If we have acid around, acid catalyzed mechanism of opening up of an epoxide looks like this. First step, the oxygen of the epoxide gets protonated, so we have this intermediate species right here. In the second step, our nucleophile comes and attacks the carbon, and then the leaving group is the opening of that ring. And then in the last step, we have the base, conjugate base from the first step, reach out and deproton that protonated alcohol right there, giving us an ether. If the epoxide is not symmetrical, it turns out that the nucleophile is going to more readily attack the carbon of the epoxide that has the more substituents. And so this is the major product when the nucleophile attacks the carbon that has the more substituents. And that's partly because in the intermediate stage, that carbon has a greater partial positive charge because of the substituents. Here's our major product. This attacks there, and then we break this open to give us this species right here, which then has to be deprotonated in the last step. versus the nucleophile attacking this carbon and breaking that bond, giving us this species, which is the minor product. In general, the nucleophile will attack the more substituted ring carbon. Under acidic conditions, the nucleophile attacks more substituted ring carbon. That's what we just said. So under acidic condition, the situation I just described is true. So we have a nucleophile, we protonate the epoxide, and then we have this species right here, and then the nucleophile attacks the carbon with the most substituent. So it would be this one here, giving us this as the major product and this as the minor product. Under neutral and basic conditions, however, the nucleophile will attack the less substituted carbon. And so here we have a situation where we have basic, so we have a much stronger nucleophile than when it was protonated as in the previous one. Reaches out, attacks there, and kicks open. And then we end up having to, in a second step, protonate that alcohol. The conditions determine the site of nucleophilic attack. So if we have this epoxide right here, this carbon will be the one that's the site of attack under acidic condition, and this one will be the site of attack under basic or neutral condition. How do we use epoxides in synthesis? Once we form the epoxide, remember that's a reactive intermediate, we can use a number of different nucleophiles in the next step. So we can react it with an alkyne, a terminal alkyne here, so that we're creating a carbon-carbon bond, making our carbon chain length longer. This is under neutral conditions, so our nucleophile is going to attack the carbon with which of these carbons attached, open up that epoxide, and the second step will protonate, giving us this new species. Here's another example. Here we have an amine, so the nitrogen acts as our nucleophile. Because it's basic, it's going to attack the carbon with the least substituent, so it's going to attack this carbon right here, opening up that ring, giving us this intermediate, which then gets protonated. And it looks like we could actually imagine transferring the proton here up to there, making both species neutral. In effect, probably. There's some acid that protonates here at the same time where there's a base that deprotonates here, giving us this final product here. If we recall back from things that we learned in Organic 1, we can remember that we added water to an alkene. Remember we had acid catalyzed hydration of an alkene. But the problem there is that we very often had a carbocation rearrangement, right? So we had a secondary carbocation with the quick carbocation rearrangement to form the tertiary, then the nucleophile added. When we did acid catalyzed hydration of water to an alkene, we very often had a mixture of products due to carbocation rearrangements. And so in order to avoid carbocation rearrangement, we can use this epoxide method. So we have an alkene, we use peroxy acid to make the epoxide, then we can open up the ring and we get a single alcohol product. When we look at NaH, if you want to understand how that process works a little bit, we're really looking at an H- as your nucleophile. So the H, because it's basic conditions, is going to react with the carbon with the least substituents, opening up the epoxide, and then in a second step will protonate. So the regioselectivity is the same as in the acid-catalyzed addition of water because the hydride ion adds to the carbon with the most hydrogens. If we wanted to form a trans-diol from an epoxide, that's simple as well. We'll just add OH- to our reaction with an epoxide. It's basic, and so we're going to have this nucleophile attack the carbon that has the least substituents, opening up that epoxide. And because the epoxide kind of sits on one side of the ring, we know that the nucleophile has to come from the other side. And so once that nucleophile attacks, kicks open that ring, the two species, the nucleophile and the O- from the epoxide ring opening, are going to be on the opposite side of the ring. Then we protonate using an acid, we get the trans-diol. If, however, you wanted to form a cis-diol, that's done in a single step. You have the alkene, you react it with osmium tetroxide, shown here, in the presence of hydrogen peroxide and water, and you end up with the cis-diol. And the way that that reaction happens is simple. Osmium tetroxide looks like this. We end up having this concerted reaction, shown here, giving us this 5-membered ring intermediate, which is called a cyclic osmate intermediate. Then you react it with hydrogen peroxide and water. It breaks the osmium species off, leaving us with a cis-diol. Epoxides are going to open preferentially in the direction that forms the most stable carbocation. Here's an example that's a little bit complicated, but if you think about it, it makes sense. If we have this epoxide here, and we open the epoxide so that we get this carbocation, we have resonance from this double bond, and it's all good. However, if we open the epoxide to give the carbocation here, we do have resonance here, but that resonance actually interrupts this very stable benzene ring. And so this carbocation is actually more stable, and this is going to be our major product. Looking at relative reactivities of leaving groups, fluorine is not the best leaving group, followed by OH. Again, remember we have to activate that. Followed by OR, ethers, but again we have to activate that. Followed by amine. It turns out that when you protonate an amine, it doesn't actually form a good leaving group. Amines cannot undergo substitution and elimination reactions. Yes, they act as nucleophiles for sure, but not so good as leaving groups. And that has to do with the pKa. The pKa of a protonated alcohol is minus 2.4. The pKa of a protonated amine is still 11.2. So that doesn't leave. Amines are very commonly used as organic bases. Here is a series of organic bases. We have all of them shown here in the protonated form. We see the ranges of the pKa's from 5-ish to 40. Amines are, however, very, very commonly used as nucleophiles, and we've seen examples of that in several places. So the lone pairs on the nitrogen act as a nucleophile to reach out and do SN2 or SN1 with a good alkyl halide or an alkyl group that has a good leaving group, with a good alkyl halide substrate or an epoxide. So the Hofmann elimination involves a quaternary ammonium ion. So that's a nitrogen that has a positive charge with 4 carbon groups attached. And this undergoes elimination pretty readily when we have a strong base. So what happens is this group leaves and one of the hydrogens here. So if we have a hydroxide ion, that's going to pick up the hydrogen here, forming water. And then this group is free to leave. And the 2 electrons from that bond hop on to form our amine. So that's the Hofmann elimination. And we simply just need to add a little bit of heat. The Hofmann elimination is an E2 reaction, meaning that it happens in a single step. If I review the mechanism that we just talked about, the hydroxide ion base pulls off the proton here. These 2 electrons hop in to form the double bond, and then at the same time the 2 electrons here hop onto the nitrogen, giving us our alkene and our amine leaving group, and then of course water. The base removes the hydrogen from the beta carbon that is bonded to the most hydrogens. The base removes the hydrogen from the beta carbon that is bonded to the most hydrogens. For example, if this is our alpha carbon, here's our beta carbon, and here's our beta carbon. The base removes the hydrogen from the carbon with the most hydrogen, so it's going to be this one right here to give our major product shown here, and then this is a minor product. And the reason is because the leaving group is poor. Remember I told you amines are not good leaving groups. Quaternary amines are better than amines, but again, not the best leaving group. So because the leaving group is poor, the transition state is more carbanion-like. Recall, alkyl fluorides have carbanion-like transition states because it is a poor leaving group. Yeah, we don't have to worry about this reaction. Sorry, I should have taken that slide out. On to thiols. Thiols are similar to alcohols, oxygen and sulfur in the same group. Sometimes thiols are called mercaptans, and that's basically because when mercury 2 is around, they can almost sequester the mercury and capture the mercury, and so that's where that shorthand name came. Here's an example of naming, but again, I do not require that you know how to name thiols in this course. We do need to know, however, that thiols are very good nucleophiles, especially in a protic solvent. And so here's our sulfur acting as a nucleophile. It can do SN2 where it attacks the carbon and then bromine leaves. Thiolate ions, meaning negatively charged sulfur, are better nucleophiles in protic solvents like alkoxide ions. The product is a sulfur analog, okay, and we call those also a thioether or a disulfide here. Thioethers are also good nucleophiles. So the sulfur can kick in, kick out, and we end up with this sulfonium salt. Sulfonium salt is an alkylating agent, so it's a way to transfer a methyl group And so here's that example. Okay, that's what I have for the remainder of this chapter. Hope that helps you with the homework for this chapter. All the homework for chapter 11 is due on Wednesday in recitation. Bye.